Ever wonder how we unlock the secrets of the universe? Like, really, how do we even begin to study forces that existed less than a second after the Big Bang?
It's a question that's fascinated physicists for centuries.
Well, today's deep dive is all about a fascinating new approach to doing just that, using quantum computers
Quantum
to
computers,
recreate
right?
particle collisions.
Yeah, it's an area where incredibly complex physics meets, well, cutting-edge technology.
Definitely cutting edge. When I first saw the title of this research paper, Collider Events on a Quantum Computer, I have to admit I was a little intimidated.
It's a mouthful.
It is. But lucky for us, we've got you here to guide us through it.
Well, I wouldn't call myself an expert.
Well, you totally are.
But I do find this research incredibly interesting. Let's start with this.
Okay.
Why simulate particle physics? Why should this matter to someone who doesn't spend their days around a particle accelerator?
Because it's not just some esoteric science project, right? I mean, there are real-world implications here.
You're absolutely right. Every time we understand, unlock a new layer of understanding in particle physics, it sort of ripples out, right?
Okay.
So advancements in medicine, material science, things like that, these often trace back to a deeper understanding of how particles behave.
At the most fundamental level.
Yeah.
So to get that understanding, we build these incredible machines like the Large Hadron Collider, smash particles together at near light speed,
Mm.
and then what?
And then comes the really hard part.
Oh.
We have mountains of data.
Right.
And to make sense of it all, to test our theories, and to really push the boundaries of what we know, we rely on simulations.
Okay, that makes sense. But this paper is suggesting that our current simulation methods, they have some limitations. I think they even said something about using code from the 1980s.
It's true.
Yeah.
While we've seen, obviously, significant improvement in computing power over the years, the core algorithms, the ones we use for simulating these particle interactions, those haven't really fundamentally changed. And as we go deeper and deeper into the mysteries of the universe, these limitations become more and more apparent.
Okay.
And that's where
quantum computers come in.
Exactly.
This is what I find so fascinating. Instead of just zeros and ones, you have qubits existing in multiple states at once. It's kind of like magic, but with math.
A bit of magic, perhaps, but grounded in some very real, very mind-bending laws of quantum mechanics.
Right, right.
And this ability, you see, to be in multiple states at the same time, it allows quantum computers to explore many, many possibilities simultaneously.
Okay.
And this makes them potentially exponentially faster than classical computers for certain kinds of problems. And that includes, you guessed it, simulating particle physics.
So we could simulate things that are just impossible, even for the most powerful traditional computers to handle.
Exactly.
Wow. This paper specifically focuses on using something called an NISQ device. What is that?
So NESQ stands for Noisy Intermediate Scale Quantum.
Okay.
And essentially, these are the very first generation of quantum computers. Think of them like prototypes, if you will. Incredibly promising, but they still come with some limitations.
Like what?
Well, first, as the name suggests, they are noisy. They're prone to errors because, frankly, we are still figuring out how to perfectly control these quantum systems and their intermediate scale because we are still working on increasing the number of qubits, which are the building blocks of a quantum computer.
Okay.
So yes, these are early days, but even these early quantum computers are powerful enough that researchers are trying to simulate something as mind-bogglingly complex as a particle collision.
And they decided to focus on something called Parton showers. I have to admit, that one has me a little lost.
It's a bit of a mouthful, yeah.
It is.
So imagine two particles.
Yeah, right.
And they're colliding at unimaginable speeds. Now, what follows isn't a neat, clean splitting into a few new particles.
Right.
Instead, it's a cascade, an explosion of new particles being created in rapid succession.
Yeah.
We call that a Parton shower.
So it's like a chain reaction, but at the subatomic level.
Exactly.
Each new particle can then decay and create even more particles.
Precisely. And it's this beautiful, chaotic mess that's incredibly difficult to simulate.
I bet.
Even with our most advanced classical computers. So this research focused on a simplified model of this process, something called Discrete QCD, which is, well, it's a model that's well suited to the limitations of these NISQ devices.
Okay, I'm not going to lie, the acronyms are starting to pile up here. We've got QCD, NISQ.
Maybe I should be taking notes.
No need for frantic note-taking. The important thing is that even though it's simplified, this model still captures the essence of how these Parton showers actually work. And to simulate it on a quantum computer, they use something called a quantum walk with memory.
A quantum walk with memory.
Hmm.
Okay, now you've got my attention. How do those work, and what makes them so well suited for simulating something as seemingly random as a particle collision?
Okay, imagine, if you will, a choose-your-own-adventure book.
Okay, I'm with you.
So you're reading along and you come to a choice, right?
And that choice leads you down a different path, and each path creates a different story.
Okay, I'm seeing where you're going with this.
A quantum walk is kind of like that. It simulates all the different paths a particle could take after a collision.
But we're in the quantum realm here. It's not just a single path, is it? It's like the particle is like exploring all those paths at the same time.
That's the beauty of it.
Hmm.
And the memory part, well, that's really crucial here. It allows the simulation to actually remember the path the particle has already taken and then use that information to influence future steps, kind of like, how real particles behave.
Oh, wow. So it's not just a random walk. There's this sort of learning process happening based on the particle's history within the simulation.
Got it.
That's wild. Okay, but the big question is, did it actually work? I mean, simulating something as complex as a particle collision, even on prototype quantum computer, just sounds so ambitious.
Well, that's where things get really exciting. They actually took this quantum walk approach and tested it on a real IBM quantum computer. It's called Ibn Algiers.
Wait, they actually got their hands on a real quantum computer. I thought those were still, like, incredibly rare, not to mention expensive to use.
They are, and that's what makes this research so significant.
Okay.
But even with all the limitations that we talked about, the results were, well, remarkable.
Okay. Don't keep me in suspense here. Did it work?
It did. It's amazing, actually, even with the simplified model and using a quantum computer that, still has a ways to go, they were able to capture the fundamental characteristics of these Parton showers.
Wow, that's pretty cool.
Yeah.
But, okay, how can they be sure that the simulation wasn't just spitting out random noise? Like, how do you even compare something like that to data from an actual particle collision?
That's a great question. They looked at specific, measurable things, characteristics of these collisions that physicists call observables. For example, they focused on event-shape observables.
Event-shape observables.
Yeah.
So, like, is it a big splatter? Is it a straight line? Like, what's the overall pattern of the particles that are created?
Exactly. You're getting it. So, for instance, they compared something called thrust, which basically measures how jet-like the particle distribution is.
Okay.
And then there's another one they looked at called energy correlation,
Okay.
which basically tells you how the energy is spread out between all the different particles.
Got it.
And what they found was that the values for these event-shape observables from their quantum simulations actually lined up really well with the data from the real particle collider experiments.
Wow, no way. So it's actually working.
It really seems like it. It suggests that, yeah, even with this simplified model, the quantum simulation was capturing something fundamental about the physics of these crazy complex events.
That's incredible. But these collisions, they don't just produce this, like, random spray of particles, do they? What about those jets, those concentrated streams of particles?
Ah, yes, you're talking about jets. You're right. Those are a crucial feature of these collisions.
Yeah.
And the researchers, well, they thought about that too. They also compared jet observables.
Jet observables. Okay, so these are, what, characteristics that describe the properties of those jets?
Exactly. Like, how many jets you see in a collision or how much energy they have,
Okay.
things like that. For example, they looked at the Durham two-jet rate, which tells you basically how often you see two jets and how close together they are. And they also looked at the jet mass difference, which, well, it's pretty self-explanatory, compares the masses of the two jets in an event.
Okay, and did those jet observables from the quantum simulations also match up with the real-world data?
To a really impressive degree, yeah.
Whoa.
Which tells us, it's another really strong sign that we're on the right track here, using quantum computers for this kind of simulation. It's honestly a testament to how clever these researchers are, and it really highlights the incredible potential of this technology. Just imagine what will be possible as these quantum computers continue to evolve, as they get even more powerful.
It's like we're on the verge of a whole new era of scientific exploration. If we can get this level of accuracy with these early quantum computers, what happens when we have systems with even more qubits, and way less noise? It's kind of mind-blowing to think about.
It really is. This research is like, it opens a door to a whole new way of doing particle physics research. I mean, imagine simulating conditions that would be impossible to create in the lab, even with something like the Large Hadron Collider.
It's like we're talking about recreating the very early universe here, just fractions of a second after the Big Bang.
It's an incredible thought.
It is. But even beyond those, like, really fundamental questions, I imagine there's some pretty amazing practical implications as well, right? I mean, the potential applications here, they seem almost limitless.
They really do. You
Right.
know, it's funny, the tools and techniques that we develop for something like simulating particle collisions, they often end up having these really unexpected applications in other fields.
It's like that old saying, what good is a newborn baby? You just never know what incredible things they'll accomplish in life.
Haha, I like that. Yeah.
It seems like we're seeing that same thing play out now with quantum computing.
Yeah, for sure. We've seen it time and time again,
Right.
right? I mean, look at advancements in medical imaging or material science, even financial modeling. These breakthroughs, they often have roots in algorithms and techniques that were, well, that were first developed for things like particle physics research.
It's amazing to think that, like, our understanding of these tiny fundamental particles that it led to breakthroughs in, like cancer treatment,
Hmm.
and now being able to understand them even better with the help of quantum computers, well, who knows what that could lead to?
Yeah, who knows?
I mean, maybe even more precise radiation therapies or like entirely new materials for building things like spacecraft. I mean, the possibilities,
It's really exciting to think about.
it really is.
And, you know, it speaks to this bigger idea that when we invest in fundamental research, when we just push the boundaries of what we know, it often leads to these innovations that we couldn't even dreamed of before.
It's like we're opening a door to a room, and that room is full of possibilities, and we have no idea what we'll find until we step inside.
Exactly.
Well, this has been an amazing deep dive.
It has.
We started with this incredibly dense, and I'll admit it, a little bit intimidating research paper.
It happens.
It does, it does. But look, you walked us through it step by step, and now we're talking about, like, simulating the Big Bang on a laptop. I mean, the pace of progress here, it's just remarkable.
It really is.
So for everyone listening, if you're feeling a little overwhelmed right now, trust me, I was right there with you. But the main thing to take away from all of this is that we're already seeing incredible results, even with these early quantum computers. Like, we're talking about unlocking some of the biggest secrets of the universe.
Mhm.
And honestly, that's something worth getting really, really excited about. Expert speaker, thank you so much for being here. You've given us a lot to think about today.
It was my pleasure. This field is only going to get more exciting, so I'm glad I could share that with you and your listeners.
Absolutely. And for everyone listening, until next time, keep those brains buzzing because who knows what mind-blowing discoveries await on our next deep dive.